or on the element, the angle is theta. Okay, so Mohr circle is what you do your calculation on. On the element is the real world. You have to relate what you calculate to the real world or not. You are wasting your time and I'm wasting your time. Are we clear? Okay, so we have to relate what we calculate using Mohr circle to the real world. So we calculate on Mohr circle is 2 theta. When you bring to the real world, you divide the angle by 2. Why is that? Because on Mohr circle, I just show you that we have point X and point Y. The angle is 180 degrees. Between point X and point Y, the angle is what? 90 degrees. Okay, Mohr circle for you. Right. So we have seen stress states where it's in tension. Okay. So now I'm going to look at a different stress state now that you will also see. So the next stress state that we'll also see on Mohr circle, right? So this is our X and this is our Y. So the next thing that we'll draw on the element is now the element is pointing in the opposite direction. Okay. So what do you see over here? So this is negative, and when it's pointing towards is under what? Compression. Okay. So when you see over here, stress X is negative. And if you don't see any arrow, stress Y is equal to what? 0. Right? When there's no arrow drawn, it means that it is equal to 0. Okay. So when that's the case, how you sketch Mohr circle now? Okay. So again, we label this, then this is your point X, and you label this as your point Y. Okay. So where is point Y when there's 0 stress? Okay. So I'm going to sketch Mohr circle again. So again, have a good habit of writing that this is normal stress. This is shearing stress, clockwise direction. Anti-clockwise direction over here at the center is 0. And over here, where is 0, right? We know that this is our stress Y. Okay. And then stress X is in compression. Okay. This is our stress X. So from here, we can label this as our point X because there is no shearing stress. Over here is our point Y. Now we can draw our element. Okay, so this element, it belongs to our X, Y plane. Okay, so now I believe you understand on Mohr circle or on the element what is normal stress and how to translate that value into Mohr circle. Okay, now the next thing that we are going to focus on besides normal stress, the next thing that we are before I say we are going to focus on normal or on shearing stress. Okay, I'm going to introduce you to terminology we always use. So this point over here is known as our stress 1, And this point over here is also called our stress 2. Okay. So what is stress 1, stress 2? So stress 1 and 2 or 2 and 2 are known as the principal stresses. Okay. So at the principal stress, right? At the principal stress, the shear stress is equal to what? Is equal to 0. Okay. At the principal stress, the shear stress is equal to 0. Okay. Now, before we go into shearing stress, right? Before we go into shearing stress, I'm going to go into a material handbook, okay? Or a handbook. I'm trying to find a book that has material properties. And we did. I don't think we see this before, but I'm going to get this property out. Right. Okay. And I'm going to copy. So I just got this, okay, from a book. Okay. So I'm going to relate what you see over here to what we just learned regarding principal stress. Okay. Right. So let's focus uh on our normal stress first. Okay. So this is a typical data handbook. Okay. Which on the first column you see the type of steel. So you have structure ASTM A36 high strength low alloy steel. Okay. You have quenched and tempered steel. Okay. And then the next column, as you can see, is the density. Then what is reported over here, okay, is the ultimate strength. Okay, so what is reported down here is ultimate strength. And what is over here is your use strength. Okay. So you realize what do you use? Okay. What do you use? We are given like ultimate strength, use strength. And then very interesting is you see this in tension. Okay. And you see the ultimate strength and use strength in tension. Okay. So if we were to sketch our stress strain curve, okay, so we have our right. So this is our strain and this is our stress. Okay. And then I'm going to sketch this out. So one value we are given over here. Okay, so let's pick this steel over here. So this is at 250 megapascal. And then you have over here, okay, and this is your 400. Okay, so this is your ultimate strength. And over here, this is your yield strength. And we are aware that when we pass our yield, this side is our plastic region. And on the left-hand side is what we call our elastic region. Okay. So now in our, so for structure design, okay, we, or in structure design, the material, okay, should not operate in the what? Plastic region. Right. So it cannot operate in the plastic region. Okay. Material must be in the what? Elastic region. Okay, remember that. So if we were to go into the textbook, okay, B and Johnson textbook, okay, and on a textbook, I'm going to, and I think you all seen this formula, right? When you're doing 2P. So let me look for the formula. Okay. Okay. So this is the textbook. And then if I zoom in, okay, if we look at loads, okay, I'm going to take this, okay, or I'm going to paste the number. It states that, again, this is from the textbook. It states that the factor of safety is equal to the ultimate stress over allowable stress. So this factor of safety is equal to stress ultimate strength divided by stress allowable. Okay. So what do you think? Look at the statement I made before, right? In structure design, the material should not operate in the plastic region. Material must be in the elastic region. But yet, if you look at the formula, you see this being what? Ultimate. And this corresponds to this point over here, which is in which region? Plastic region. Okay. I'm going to stop here for 10 minutes. We take a break. We come back. We focus. We are going to talk more about this. Okay. Take a 10 minutes break.